Hi, everybody. This video here is to um, support Lab 4, and the circuit itself is not particular to Lab 4, but in Lab 4, you're using the Tektronix oscilloscope instead of the Multisim oscilloscope. So in this video, I'm going to show you how to use the oscilloscope, and the reason I think this is so valuable is because this Tektronix oscilloscope is a simulated instrument that is giving you a front panel identical to the actual instrument in the lab. So by getting you to use this instrument, you can familiarize yourself with the settings that you need to make to the oscilloscope as they would be on the oscilloscope. So not as perfect as being in the lab, but pretty good for this situation. So how I got this, this oscilloscope into my circuit, I went to the Simulate menu, Instruments, and down at the bottom here, Tektronix oscilloscope. Okay, that's how I got it. And I put it in here with my circuit. Now this circuit, again, is not the Lab 4 circuit. It's just a simple circuit that I put together just to show you some features of the oscilloscope. Notice on this circuit, I have an AC voltage source, a DC voltage source. These two sources are powering two resistors in series. I've hooked up the oscilloscope, so this is the icon of the oscilloscope where I would make the actual connections, but when I double click that, it shows me this front panel here. Notice that, let me clear my scribbles here. Notice that channel 1 is connected here. Channel 2 is connected here. And the important thing to remember about scope channels is that both scope channels are referenced to ground. And so that's why this ground connection here is connected to the ground of our circuit. So channel 1 is measuring this voltage. Channel 2 is measuring this voltage. And so you can see that I can't measure the voltage across R6 directly with the oscilloscope because I cannot put, I need another color here, I cannot put the ground lead here, okay? If I were to do that, I would actually short this part of my circuit to ground because the ground of the scope and the ground of the power supply would be connected externally. So I can't do that. I have to always put the ground leads of the scope to my circuit ground, which is here, okay? But the scope does have a math setting which will allow us to subtract this channel 1 from channel 2. And if I did that, that would give me this difference. Okay, so we'll take a look at that once we've got our scope all set up. The other thing to remember is that, you know, these channel 1 and channel 2 connections on the scope, they're right here, right? So this connector is going to branch out into a red lead and a black lead. And this one is also going to branch out into a red lead and a black lead. The two black leads have to be connected to ground, right? They're both going to be connected to ground. And then for the red leads, I would put my channel 1 there and my channel 2 there, right? But I should connect both those black leads to the ground point of my circuit, okay? Now, first things first, I made this mistake while I was setting up for this video. I turned on my oscilloscope and I didn't see anything at all. And it was because I didn't have my simulation running. I'd stopped my simulation for a second. And so I have to remember my simulation has to be running so that my power supplies are on and I'm getting some signals there. And the nifty thing about this scope interface is that now we are going to push buttons and turn knobs as if we had the real scope in front of us. And this is a picture of the real scope, so perfect. So I'm going to turn on the power button, and there is my scope screen. And so let's go over, before I start setting up the settings, let's go over what some of the knobs and selections mean, and let's think a little bit about our circuit, because one of the most commonly used buttons on the oscilloscope, probably second to the power button, is this autoset button right here. Now here's the thing, I don't want you to use this button, okay? And you can ask your lab instructor about that, but if you're in Brandine's labs, I don't want you to use the autoset button, right? I want you to think about how you would set up the circuit so that you don't need to push that button, right? How would you set up your oscilloscope knowing the details of your circuit so that you don't have to press the button? So I'm going to say no to autoset, right? It's not that you can't ever use autoset, but if the only reason you're pressing autoset is because you don't understand how to set up the scope, that's not good, right? So let's get that knowledge right now. And to think about how we would set up our scope, we have to understand some of the main settings. So there's a volts per division setting and a seconds per division setting. So the volts per division setting is saying how many volts on the vertical scale is one of these major divisions. And the time per division is saying how many seconds is one of these major divisions on the horizontal scale. So remember that your scope is plotting voltage according to time, right? So these settings down here at the bottom, this channel 1 where it says 2 volts, is really 2 volts per division. And we can change that, right? If I grab the volts per division knob and I turn, you know, I can change that. So now it's set to 10 volts per division, okay? So I would change this to 10 volts per division. So I can change that setting, and notice that the time scale is set to 2.5 nanoseconds per division. So what they don't display on the screen here is that the unit is actually per division. And when they say per division, it's one of these big squares, okay? Not the little tiny ticks, it's a big square. And each of the big squares is actually, with the tiny ticks, is divided into 5. So when you're measuring waveforms, keep that in mind. So I need to decide what to set the 10 volt and the volts per division and the seconds per division scale to. And how I decide that is I look at my waveforms. So here's my AC waveform, and there's my DC waveform. DC, it's 2 volts. AC, it's 3.5 volts RMS. Okay, so that's the RMS value. To think about how much room I might need on the scope screen to display it, I want to convert that to peak-to-peak voltage. So this is equivalent to 2 times root 2 times 3.53 volts peak-to-peak, which is 10 volts peak-to-peak. Okay, so we're expecting to see a waveform that is 10 volts peak-to-peak with a 2 volt DC offset, right? And what does that mean? It means our AC waveform is a sine wave. It's 10 volts from here to here. However, the AC waveform is referenced here to 0 volts. Adding in the 2 volts DC actually shifts this waveform up by 2 volts. That's a terrible drawing, but the waveform would be shifted up. It would still be 10 volts peak to peak, but the center of the peak to peaks would now be sitting at 2 volts, okay, because it's had that DC component added to it. So So that, knowing that it's 10 volts peak to peak with a 2-volt offset, I can think about what I might want my volts per division to be. And right now my volts per division is at 10 volts. So that means my waveform is going to fit into one of these squares, right? I don't know about time for now, but top to bottom, it would fit into one of these squares. It's really hard to visually take a good measurement from the scope with the waveform that small. So what I might do is take this setting and change it to 2 volts per division, because then my waveform peak to peak would take up 5 divisions, and it's offset by 1 division, and top to bottom I have 8 divisions, so that's enough room to put my waveform quite large on the screen. Okay, so so I'm going to remember that 2 volts per division. Let me clear my drawings, and I'll go ahead and turn that knob now and set that to 2 volts per division. So I'm just clicking in and turning that knob. So I'm set to 2 volts per division. That's great. But what about this time scale, right? This time scale here, what do I set that to? And to figure out what I set that to, I have to look at the frequency of the waveform. Now, my input voltage is 1 kilohertz. This circuit is not going to change the frequency any. So no matter where I measure, it's going to be a 1 kilohertz signal. Now, a frequency of 1 kilohertz is going to be equivalent to a period of 1 over that frequency, which is 1 millisecond. So, if I want, say, to get, 2 cycles of my waveform on the screen, and I know that the screen is 10 divisions across, 10 divisions, that means one of these cycles would take up 5 divisions, and one of these cycles is 1 millisecond. So 1 millisecond divided by 5 is 0.2 milliseconds per division, right? Divided by 5 divisions. So that means that I need to set my my horizontal seconds per division scale to 0.2 milliseconds per division if I want one cycle to take up 5 divisions, so that I can get 2 cycles on the whole screen, which has 10 divisions across. Okay, so so let me go ahead and do that now. I'll clear these calculations. I'm going to click and drag on this horizontal seconds per division knob. Actually, I'm not going to do that yet. Let me not do that yet. So I figured out what it should be. Let me put it back to what it was. Let's think about something right now before I play with these settings. Right now, we don't see a waveform on the screen, right? And the circuit is running, it's connected. We should see a waveform. We don't see one. So in that situation, the first thing I would check is, have I turned on that channel? So the channel 1 menu button here, notice if I click it, I've actually turned off channel 1. I don't see any of the settings for channel 1. So let me turn it back on. I see the settings for channel 1. I see that I'm on DC coupling. Let me draw on the screen. DC coupling right here, which I want. Also note that my volts per division is set to coarse, which I want, because it means when I'm changing this value, it's changing by standard increments, like 1, 2, 5, 10. If you change that to fine, you can change your volts per division to actually, decimal points of, like 2.3 or something like that, right? And I don't want to do that right now, so I'm going to leave that to coarse. And I don't want to invert the signal, so that should be off. So all of that looks okay, but I don't see a waveform. Now, the one thing to notice is this stop here. I have actually, prior to showing you, I had actually pressed the run stop button. And so what I need to do, I need to go over here to the run stop button and press it so that that the scope is actually running and will pick up the signal. You use this run stop button, you can use it to do a bit of a freeze frame. So if the circuit is jumping a lot and it's hard for you to look at it, to read the signal, just stopping it will freeze the frame and you can see it. But there are a few other ways to get the signal to settle down, and I'll show you one of those a little bit later in the video. So let's press the run stop button and notice, yeah, so here's my screen jumping like crazy. And if I stop it again, I do actually have a signal there, but it looks really flat. It doesn't look like it's oscillating like a sine wave, right? So the other thing I have to remember is, oh, my time per division scale is on 2.5 nanoseconds, and I said I should be on something like 2.5 milliseconds per division. So let me go ahead and change that. I'm going to grab the horizontal seconds per division scale and I'm going to start turning it. Now remember, 0.2 milliseconds is 200 microseconds. Oh, I'm going the wrong way. Okay, I want 200 microseconds. Oh, I had it. There it is. Okay, so I'm not very good at turning that knob, but there we go. Obviously, there's some limitation to interacting with the screen and the pen that I have, and my coordination. But there we go. So this this 200 microseconds is the same as 0.2 milliseconds. Okay, and so my waveform is still not there because the stop button is pressed. So let me run. And there you go. There is my waveform. Now, and I do have two divisions on the screen, just as I suspected. Now, my waveform is not in the center of the screen. If I want to change the position of it, there's two knobs that will help with that. There's the position knob for vertical and for horizontal. So let me change the vertical position, and you can see I can move the waveform up and down. I can move it side to side, and moving it side to side can be handy when you want to take a measurement. So notice I've lined the peak to peaks up there, and I can see that from one peak to another peak is 5 divisions. So let me just stop it. Oh, show it. If I stop it, it won't show the whole thing. That's a little bit different. Okay, so let me draw on the screen here. From here to here is 5 divisions, right? And 5 divisions at 200 microseconds per division is 1 millisecond. Okay, so we can see that our period is 1 millisecond for this waveform. That's a frequency of 1 kilohertz, exactly what we should expect, right? And I can move the waveform up again. Oh, I can, if I want to take a peak-to-peak voltage measurement, it's a little bit awkward to read right now because it's in the middle of the major division. So I can position the bottom of the waveform at the start of a major division. And then I can count, it's a little bit off there, but I can see I have 1, 2, 3, 4, 5 divisions high times 2 volts per division. So here to here is 5 divisions times 2 volts per division. Divisions cancel out, and that is 10 volts peak to peak. Now, the one thing that you can't see on there is where's the ground reference. So let's change the coupling to ground coupling, and you can see, oh, there where the 1 is pointing with the little arrow, that's where my ground is. So let me position the ground so that it is, I'll put it on, that line's okay. I want to make sure there's enough space below and above for my waveform. So I've positioned the ground to that 3rd major division up there, and then I'll put it back to DC coupling. And notice you can see that the waveform is actually shifted above ground. So the center, the ground line is here, but that's not the center of the peak to peak of the waveform, right? The center of the peak to peak of the waveform is here. And so that is that 2 volt, that's not a good color, hang on here. This is that 2 volt DC that shifted that waveform up by 2 volts. Okay, so when I'm on DC coupling, I can see if I've got a vertical shift in my waveform. So what we also call it a DC offset, right? So I can see if I have that. Now, if I switch this coupling to AC coupling, you can see that now the center of the waveform is actually where the 1 and the arrow is, because on AC coupling, the DC component is removed, and you don't know where it is with respect to ground. But that setting is actually useful if you want to measure a very, very small AC waveform that has a large DC offset. So, so right now, you know, the size of our AC waveform is very big compared to our DC offset. If it was the other way around, and we had a very tiny AC waveform that was shifted up above ground by a large amount, it would be very hard to read that peak to peak on the scope without, you know, first cutting out this DC and expanding the scale to see that, okay? And that's something that you can do in the lab when you're looking at some of these waveforms. So I'm going to clear my drawings here. The other thing that I want to show you is the trigger level. So there's the trigger menu and the level here. These settings, if I press trigger menu, I can see that it's edge triggered, the source is channel 1. Now this scope's not jumping if I put it to channel 2, but normally if I were to put the source to channel 2 with nothing connected, oh wait, yeah, I do have channel 2 connected. Okay, so let me put it to channel 3. Notice that because I have nothing connected, I have nothing connected here on channel 3, with the trigger being trigger source being channel 3, the channel 1 waveform's jumping all over the place, right? So what I would do is put that source to my biggest waveform that's connected. So right now I've got it on channel 1. And sometimes the trigger level, I'm turning the trigger level wheel, and you can see, I'm going to circle it for a second, this little tiny arrow moving up and down, that's the trigger level. If the scope happened to be set so that trigger level is outside the range of my waveform, the scope won't be able to trigger very well. So you can see again, if I move that trigger level way up here beyond the range of my waveform, now it's jumping all over the place, right? So what I want to do is change that trigger level back down to be within my waveform, and that's steady. Okay, so the next thing I should show you here before I end this video is is the fact that I'd forgotten about that for a bit. I did actually connect a signal on channel 2, right? So let me turn on channel 2. So I've turned on channel 2. Now nicely this scope has color. So it's showing me channel 1 is yellow and channel 2 is blue. And you can see that channel 2 looks smaller on the screen compared to channel 1. Now that alone is not surprising because channel 1 has the full supply voltage and channel 2 just has the voltage across this resistor. I do expect it to be less, but the one thing that you should be careful of is notice that channel 1 and channel 2 are not on the same volts per division. So channel 2 is on 1 volt per division. Okay, and that's not a bad thing. It's just something you have to be aware of when you're looking at the scope. And if I want, I can position channel 2 to be, you know, in a different position compared to channel 1. So quite often what I would do is I would put channel 1 above, oops, and I would put channel 2 below, right, when I'm taking measurements. And then in my mind, 1 is always above and 2 is below. Sometimes you might want to match up the grounds of channel 1 and channel 2, especially if you're taking a reading between shifted waveforms and you want to take accurate measurements, you might do that. Now, if I want to use the math function, I should put channel 1 and channel 2, I need to put channel 1 and channel 2 on the same scale. So I'm going to set channel 2 to 2 volts per division as well. Oh, I'm changing the wrong thing. I'm changing up-down position. I meant to change volts per division. So volts per division, I'm going to set also to 2 volts. So now both channels have their volts per division the same. And the reason I set them the same is because I want to use the math menu. If I do channel 1 minus channel 2, I can get this voltage here. So, but to do that, I need both channel 1 and channel 2 to have the same volts per division. So let me press the math menu. Oh, I'm still on my drawing mode here, hang on. Okay, I press the math menu and you can see now I have a red signal, which is also has its ground shown by this little M off to the side. And it is off positioned too high at the moment, so I'm going to bring it down. I'm going to bring it down by bringing the channel 1 waveform down. Okay, so now I can see them. I can see them all on the screen there. And the first thing I noticed looking at this is that it doesn't seem to make sense. It's like I wanted channel 1 minus channel 2, but then I realize when I look at the menu, I've selected the plus operation when what I wanted was the minus operation. So let me select the minus operation and reposition my waveforms, and now I can see that the red waveform is actually smaller than the yellow waveform, and that makes sense because the red and the blue waveforms here should add up to the yellow waveform. Okay, and they do. But I could pick, you know, when I pick a different math operation, there's FFT, there's plus, right? And so check that, because quite often we're using this setting for subtracting channels, but you have to make sure you've selected minus there. Okay. And so one last thing before I end this video, I'm going to turn off the math menu. I should show you how to read a smaller waveform like the measurement there on channel 2. What I'm going to do is zoom in on channel 2 by changing the volts per division to something smaller and reposition channel 2 so that I can see it fully on the screen. With that volts per division setting, I can't, so I'll have to go to 200 per division. And then I will position channel 2. So I've positioned channel 2 so that it's resting here. It's 200 millivolts per division, and the top of it is there. Now, to read that a little bit more accurately, I might shift it horizontally so that I can get the peak of that waveform to cross the ticks a little more clearly. Actually, it's easier for me to see there. So there's 5, 3, 4. Oh, this scope has 4 ticks. That is rough. I'm so used to reading 5. But okay, so I can see that I have 1, 2, 3, 4.5 major divisions. So I have 4.5 divisions times 200 millivolts per division. So that is 0.9 volts peak to peak is my peak to peak measurement for channel 2. Okay. So play around there in Multisim with the scope and play with the settings and make sure that you really understand how to set the scope up without pressing that auto set button. Okay.